and it's an honor to introduce Dr. Kamble. So Dr. Swapnil Kamble is a biotechnologist. He did his PhD from National Center for Cell Science from Pune, where he developed a panel of biomarkers for molecular classification of high-grade serous ovarian adenocarcinoma. He has published 10 research papers in national and international journals and 6 book chapters. He is currently associated with Department of Technology as assistant professor. He is also a reviewer of PLOS and Elsevier journals. His research interests include discovery of anti-cancer molecules from high-value medicinal plants and development of biomaterials for transdermal drug delivery approach. He works in collaboration with healthcare startups like Oncoker India and Newman's Phytovigyan, where he has evaluated formulations responsible for management of side effects caused by chemo and radiation therapy. The product Rican Plus and Rican from Oncoker India is now being commercially marketed. So, and I would also like to add, Dr. Swapnil Kamble is a great colleague to work with, and he is a great motivator to all his students. So I welcome Dr. Swapnil Kamble to you, and I request you to start your presentation. Over to you, Dr. Kamble. Thank you.
Thank you, Bina ma'am, for the wonderful elaborate about myself. Thank you so much. And I welcome all our participants for this session. And let me just share my slides.
The presentation is visible.
Okay, great. So thank you, ma'am. So good morning to one and all, and I'm here to talk about sustainable biomaterials. And on this platform of AICT ATAL FDP program on sustainability engineering. Now, while we have a wonderful sessions on various aspects of sustainability, whether it was nanosciences, like yesterday or day before, wastewater, or a day before that on solar energy, all of these talked about sustainable methods and processes. Now I'm here to discuss about sustainable biomaterials. So before going into biomaterials, I want you to tell me about what you know about biomaterials, and I want you to either log in to menti.com and enter this code, or I've just shared this link on the chat box, which you can just click on it and tell me about it. I will just share what you know. You have to just talk about, mention 3 points that you know about or you want to know about biomaterials. So I request the participants and my fellow colleagues, speakers to just log into this website, just enter this code uh, at menti.com or click on this link that you can see and just type in what you know about biomaterials. You just have to enter any 3 keywords that are available to you. These 3 keywords could be anything that you want to know, what you consider is a biomaterial, and so on and so forth. Let's have this activity for Let's keep this dashboard open for a couple of minutes and then we will take this ahead.
Sir, please unmute
Dr.
yourself.
Kamble, you are unmute yourself. You are on mute, Dr. Kamble.
Sorry, thank you, sir, for pointing it out. Someone has just mentioned that their ideas on biomaterials as obtained from biooriginal or materials like chitosan or lignoc. That's true. I would request more for the participants to share what they know about or they think what biomaterial is about. Okay, someone typed in something which I cannot understand. Let's see. Are you able to get the page with the link? If anyone having any issues, please do let me know. Yes, Piyush, you have raised your hand. Anything you want to ask? Okay, I want to know anything, whatever you think. Like, yes, someone just wrote enzymes, mass, right? Produced from living things. Absolutely good. Couple of more participants, if they can share. We'll have some good. I'll have some idea at what level we need to discuss this. Obviously, I do not expect you to be expert, but when I say biomaterial, what can you make out of it? Okay, so maybe we have some participants who may be ghosts who do not or who are shy. So let's take this thing ahead. So I will talk about something from the basics about biomaterials, and then you will have some idea what it may be about. So let me switch back to the PowerPoint presentation, and someone please tell me if you are able to see this presentation.
Yes, there is visible.
Yes, thank you so much. So, what we looked at from this small activity is there are some of you know about what materials could be. Uh, Many of you suggested one of the participants suggested it is of biological origin. Yes, that is true. And a material could be interacting with a human. That is what the whole idea of biomaterials is. So what we are going to discuss today is about the basics, how this biomaterial is actually interdisciplinary in nature, what are the materials involved in this biomaterial domain, what are the current research which has been done so far and how it is evolving, what are the previous generations and what is the current generation that we are in of biomaterials, the integral components of biomaterials and the principles which make a material actually a biomaterial are the integrals of biomaterial. Then certainly the types of biomaterials. There are many types, 4 to 5 types, of which I'll be emphasizing more on the polymer because that is where I work, and others which many of us are aware, passively aware, but maybe have not recognized it to be a biomaterial as yet. And you may be surprised that some of the components that you may be already aware of. And if we have this same survey at the end of the session, you may recognize that you know many things about biomaterials. So biomaterial is anything which is non-living entity which has to interact with a human body so as to have a functionality with respect to either enhancement of a function of the body with respect to either a treatment or a condition or for a diagnostic purpose. Now, this is a very broad subject that I have talked about. If you look at historically, the first time biomaterial as a term was used in a conference by Professor Williams in 1987, almost like 35 years back, and where he said a biomaterial is a non-viable material used in a medical device and which is intended to interact with the biological systems. Now, non-viable material is something non-living. A medical device is something that you may be aware of, and it is supposed to interact with the biological system. Biological system here, we are broadly talking about us as a human body. And when we talk about a medical device, the medical device is also interacting with the smaller entities of the human body, like the organ or the skin, if it is interacting with. So these are the biomaterials that he talked about. Now, over these different decades, 3 to 4 decades that we have seen of biomaterials, the definition has become a bit broader. And Biomaterials Journal, coming from the House of Elsevier, defines biomaterial as a substance which is engineered to take a form, which alone or as a part of a complex system can be used to direct by control of interactions with components of the living systems, the course for any therapeutic or a diagnostic procedure. Now, this is very long definition, but let's try to break it up. So, what we know is it is definitely a material. Now, this material is engineered, it is developed in a way that it takes a specific shape, size, form, consistency, texture, which may itself be a part of a bigger complex machinery. This complex machinery can be used either directly or remotely controlled in some way so that it can interact with components of the living system. Like, for example, if I am a living system, it has to interact some components of me, let's say my arm. It has to interact with my arm, it has to interact with my leg, maybe it has to interact with my heart or an eye, whatever. So these are the interactions that these biomaterials are supposed to talk to. And this application is specifically for therapeutics or for diagnostic purposes. Now, this encompasses quite a broad range of arrays of materials that we are talking about. So, moving ahead, if we talk about all these things, we should also consider the focus of sustainability of these biomaterials in the ecosystem. Now, sustainability per se, like Dr. Adinath previously mentioned, that we have not inherited Earth. This Mother Earth is not ours. We have actually borrowed it from our children, basically emphasizing that we cannot exploit it to the levels that we have exploited, the effects which we are already seeing. Many of you may have experienced climate difference within this week, being cold in the start of this workshop and relatively warmer as we are moving towards the end. And it is January, so it's not supposed to be, right? So we are already seeing the effects of these changes, and therefore we are talking about sustainability as a concept wherein we have borrowed time from our children to make use of it, make use of various resources that are available to us. So, sustainability as a definition talks about development that meets the needs of the present without compromising the ability of the future generations to meet their own needs. Now, here we are talking about maintaining a balance, and when we are talking about making new biomaterials, and considering this field is still young, 30, 40 years is, we can say it is pretty young in itself. let's not make some extensive materials which are going to be very destructive to the ecological system, but rather make it in a very sustained manner. A system which will allow making materials which will not only help us, but the process of making it will be not so energy and material invested. So what is the need of this biomaterial and where do these concepts come in is basically in the domain of tissue engineering and regenerative medicine. Now, tissue engineering and regenerative medicine is the thing that we are going to discuss today as a whole. And tissue engineering and regenerative medicine, which are referred to as term in short, can be divided into certain segments. The first segment is tissue engineering. And what is tissue engineering? It is a combination of cells. The cells, usually let's talk about human cells, a scaffold which will be artificial architecture in which the cells can sustain, and the growth factors which are going to allow these cells to grow. So these growth factors are components of the living system, which are secreted by other cells and which allow healthy growth and direction for a cell to grow. Like as we are growing older, as we age, we can see specific type of growth factors are released at different time points. For example, when we are young, when we are from the infant stage to the child stage to the adolescent stage to the adulthood, different growth factors are released in different proportions so that the body is growing in the way we have seen it. These growth factors are also the ones which are responsible for day-to-day activities. For example, if I cut myself in the kitchen and there is a wound, the wound healing which has to be induced is also associated with local growth factors which are released by the skin so that my wound is healed. So these factors with the cells in the architecture called a scaffold, they together comprise a domain which when combined with the concept of regenerative tissues becomes the entire concept of tissue engineering. Now consider this entire bracket of tissue engineering, which includes the cells, scaffolds, growth factors, and the regenerative tissue where I'm talking about. Consider the wound I was considering. In this wound, the tissue has to fill in the gap which was induced by the cut. And this filling has to be by the cells themselves, some materials which are released by these cells. And during this process, what we see is a very interesting phenomena called as the wound healing. Now, we are considering this tissue engineering as a separate entity, and when we combine it with regenerative medicine, which it itself includes tissue engineering and a therapy aspect associated. Now, this therapy aspect could be gene therapy or immunomodulation or a cell-based therapy, and basically for the entire tissue or the organ so that it can regenerate. Now, wound healing of the skin is a very simple way to look at regeneration. In our body, there are various tissues, various regions which require regeneration. Because once we attain adulthood, when our body mass index is almost proportional and fixed, we need to continuously establish the components which are lost as things are aging. Various components of the body, especially the proteins, they are continuously degrading, and at the same time, they are being replaced by the new proteins which are formed. So this regeneration cycle is the one which makes me look like the way I am, the way you are. And we are only aging on the superficial as well as interior levels. There is one organ in our body which can be regenerated in a very large proportion. Some of you may be aware it is liver, which is claimed that nearly 30% of the liver can regain to make relative 100% of it. Meaning, if I have to donate my organ to someone else, I can donate up to 70% of my organ and still attain the same functionality in a couple of days when my organ regrows. Isn't it a very fascinating thing to understand that, yes, someone needs an organ, I can donate it. Now, this organ donation per se is human entity transferred being to another human entity, one organ being transferred to another organ. This process is not regeneration. But the host who has donated the part of the liver has to regrow it, and that is the organ regeneration that I'm talking about. Now, this process is not feasible for each and every organ that we have. For example, if I have an eye injury, I cannot regrow my eye. It's a very complex system, tissue organ that we have as eye, and it cannot be regenerated the way liver can be. So what are we going towards? So what we are going towards is a process of aging wherein during these various decades of our life as humans, we have evolved to a level wherein we control a lot of our environment. We control the way we are, how much amount of food we can eat. We can also eat excess food. And there are also conditions where we can control how to get rid of it. Now, when we look at term as such in its entire entity, it is basically coming out from material sciences, biomechanics, cell biology, and medical sciences, all of which are combining to each other to make a functional organ. Why we are looking at a functional organ? Because you now know, every one of us are already aware of it, that our life expectancy has increased. If we look at India, when we were just independent, a new country, the life expectancy was near about 50 to 55 years of age. If today I am 55 years of age, then I can say that I am supposed to die in my next year. If it was way back in 1945, 46, 47. But if you see any person about the age of that bracket, every person who is about the age of 60, you are seeing that the efforts which have been taken by you, by me, all the scientists, researchers, engineers, technologists, technopreneurs, entrepreneurs, we have increased our life expectancy. If we look at India, the average life expectancy itself has risen to almost 60 to 70 years of age. And we are going to be a population very soon, maybe by 2050 or so, wherein we have the oldest populations of the world. Right now, the oldest populations of the world are in Japan. We have the youngest ones. By 2050, we are also going to be the country which will have the highest number of people above the age bracket of 45 or so. So, does it mean that we are compromising somewhere? No, we are increasing our life. That is what a smart organism can do, right? But at the same time, the biological system, also have their own clock. They suffer their own system failures, and that system failure should end with the death of that organism. If these conditions are not met, we end up with mutations, and these mutations can lead to various diseases. Most common of them is cancer. Many of you are aware, cancers of different types occur at different life stages. Different life stages have been more associated with long-term mutation accumulations. And very recently, till 2000, rather 1990s, it was assumed that cancers are the disease which happen at an old age. And childhood cancer was not a concept as yet. But now we know of these systems that yes, childhood cancers do occur. And these are all because of mutations. These mutations are not supposed to sustain the body. These mutations should actually kill the organism. But as humans have evolved, we have evolved our science and technology to the level where we can take care of these disease conditions. Now, what we are looking forward to is we are going to have a lot of requirements of materials, specifically prostheses, which are going to help us overcome our limitations. Yesterday, Dr. Amalnekar talked about having nanomaterials in prosthetics. Prosthetics are artificial limbs. You may be aware of it. We have Olympics specifically for that. Para Olympics has a specific dedication of running as well. And people with different disabilities are participating. And India has got one of the highest number of gold medals and overall tally in that Olympics held very recently. So how is all these things happening? You have seen these guys. You have seen people throwing javelins. You have seen people boxing. You have seen basketball happening with these people. So what are these materials coming out? These are the prosthetics. These are the biomaterials that I'm talking about. So these are the interacting phases with which we can see, yes, the effects of materials have been impacting the human life. Some of the fastest people, some of the they are using prosthetics. Like we have one of a very renowned marathoner, uh, who was actually who is infamous for killing the spouse basically because of using the same blade which we used to run. So these are the conditions which we are enhancing to people's life by using materials. Now, when we look at material sciences and term as such, it is divided into three different categories, three strategies to say so. First is the cell biomaterial complex system, in which the cell, the individual entity of the body, they are implanted into the body to repair and regenerate the host tissue. So what I'm talking about, let's add a human cell to the same host, which is going to improvise its own function. The second strategy is to make a stem cell like a transplant. So transplants are not always from one person to another person. They can also be from one side of the person to another side of the person. For example, if I get a scar on my face by for whatever reason, whether it was because of a wound or I got some scratches or some disease, I can take out the skin from my other part of my body, which is usually covered, and then I can transfer it on my face, right? So that is feasible. So this is transplantation from the self body to the other part of the body. There is also a possibility of instead of transferring the entire tissue which was already pre-made and taking only the stem cells, which can lead to formation of that final product, the final, let's say, facial features. I will just take those cells and induce to give me that concoction wherein I can have the kind of cell features which are expected, like the skin. So that is called as a stem cell transplantation. The third strategy is to use a biomaterial system. This biomaterial system is going to be compatible with the host. It will not cause any side effects, and it is going to integrate itself into the body and make it function. Now, many of you may be aware of it, right? You are aware of many components which can be put in to replace certain components of the body and make it fully functional. For example, if you know anyone, or if I have a fracture, in order to maintain a good stability and very good functionality of the body, I can use nuts and bolts to hold my bones together, allow it to naturally heal, get rid of the bone, nuts and bolts later, and then fill it up. You know about this, right? Many of you may are already aware of these concepts, and you may be knowing people around you who have actually experienced it. You may be also aware of people having stents in the body. You may be also aware of people having heart blockages or heart valves changed. Pacemakers, they are again biomaterials. So these are the concepts that you are already aware of, and these are the materials that have been so far been made. So if I can conclude, what is a biomaterial? It is a substance which is engineered to interact with the biological systems for a medical purpose. Now this medical purpose is very specific. It could be therapeutic or it could be for diagnostics. Now, when we look at biomaterials, it is coming into its own science, and this biomaterial sciences basically addresses the properties and applications of biomaterials, whether they are synthetic or they are natural, and they are supposed to be continuously in contact with the biological system. Biological system is again, like I have repeatedly said, it could be the skin, it could be under the skin, it could be a bone, it could be a muscle. These things are the ones which are going to interact with, and all the materials will be referred to as the biomaterials. One simple example in this cartoon that you can see that the biological aspects and the material sciences, both of which are based upon chemistry and physics, they are going to researched upon. The materials are going to be made. These materials are going to be then engineered into specific shape, dimension, with some specific properties. Like in this case, you can see femur like a bone replacement, a hip joint, which is very known now. And then following it with some studies, these studies are basically preclinical and clinical studies. Here we can see that we are using it on a small animal, This preclinical testing involves evaluation of various parameters, whether the material is toxic, whether it is stable, whether it can sustain the weight of the organism, what all effects can it have, will it degrade over a period of time or not. All these things are looked at in the preclinical and the clinical settings. Then once it is done, it is going to be approved by the regulatory bodies. Like many of you will be aware that DCGI is the one which controls the drugs. In a similar way, we have cosmetics also being regulated, food being regulated, and in the same way, we have materials which are also to be regulated. Well, these materials are coming in a domain of practice as to interaction with the humans, it has to be clinically applied. And that is where the doctors, surgeons, medical people are going to come into picture. And it has to be in a way that it can be sustained. It cannot be a just one-off activity. Like we have limited one-off activities in research, but if it has to become a sustainable model, it has to be commercialized. So this is a complete cycle that you see here of starting from researching from fundamentals, discussing it with various researchers coming in the domain of chemistry, physics, material sciences, biology, and so on, developing a product prototype, evaluating it with some animals, testing it out. Maybe it has to go back again, and then once it is ready, it is going to go for the regulatory approval and the commercial aspects. Now, let's talk about how these numbers actually come to. What are the domains that we are talking about? So here I'm just sharing a very recent data that has come out in the fourth edition of a Biomaterials introduction book. And here you can see, when you look at the skeletal system alone, the skeletal system I'm talking about the joints especially, and you are aware many of the joints need to be replaced over a period of long age because of during the elderly phase, joint replacements, especially hip, knee, and the shoulder replacements are pretty required. They may also be required due to injuries which are faced. Like you may have, that while during various other activities, like let's say fight, like in a war or sports, there are injuries and these or accidents or mishaps which require replacement of certain joints. So these joints are going to be replaced, and when you look at what are the materials used, so we have titanium, alloys like cobalt, chromium, polyethylene, alumina, zirconia. These are the materials which are used, and just look at the extreme right side. You see the market. Look at that figure. It is 16 billion global market in US dollars. It's a huge number. Look at how many units it is about. We are talking about 4,100 units only. Only. Okay, it's a fraction of the population that we have. A fraction of total people wanting and willing to take it but can't afford it. But still, it is a huge, huge market. There are other examples within the skeletal system which are listed here. Small, some basic like plates, screws. Like I give an example of replacement of a bone, or if I have a fracture, I need a plate to be inserted. It needs to be held back with nuts and bolts, rods, etc. And these are again quite important. They are required for the functioning of the body. The bone can heal itself. It's one of the good parts of the body that we have stem cells across our body, which will allow the healing to happen. But we are not happy with that. We want it to be enhanced. We want time to be reduced, for which we require an internal support system so that the function can be attained quickly. And that is where the skeletal system is coming as very important one. And you can see that we have spine discs also coming up. We have bone defect repair to be coming up. And when you look at the central column that we have of biomaterial which is used, you can see it is not a single material which is used. It's not a titanium plate that I'm putting everywhere. It's not zirconia that I'm putting everywhere. They are there. Along with there are other components as well. So what are these components? Why are they required? Are they required all the time? So these things come through the previous approach that I just shared. What is the compatibility? How good it is? Is it required? Do I need titanium for everything? If I break my tooth, do I need titanium replacement, or can I use another replacement? These are the some things that we need to be aware of. Another example is in the cardiovascular system. In the cardiovascular system, if you are aware, the highest number of bed occupancies in India is because of cardiovascular diseases. Highest. Okay, so if you go to any hospital, any big hospital, the number of beds which are occupied, the number of diseases which is happening is because of this CVD, cardiovascular diseases. These are the major diseases of India. I'm talking about. This is as recent as yesterday. You can talk about it anytime on this, and you will come to know what are the issues associated with cardiovascular system. Commonly, you are aware of it, about the cholesterol levels, the cholesterol fats sticking into the veins, preventing the blood flow, causing heart attacks, strokes that we are commonly referred to as. And then there is a procedure which is to be done, which is called as open heart surgery or other things. As we age, the rate at which our heart uh, pumps our blood also slows down, because of which there comes a requirement of pacemakers, which will maintain that electric signal required for pushing in the blood and out of our heart. So these things are something that you're aware of already. And when you look at these things, just look at the cost and the market on the extreme right side. It is 9 billion and 10 billion respectively. And it uses a combination of materials which are possible, quite a few of them. And these stents are not one single entity. They come in different shapes and size. I may be requiring it in left valve, you may be requiring it in the right valve. Anything is possible. So there's a huge combination of things which are coming in the picture. So all these things are pretty required, and you can look at the numbers which are already there to showcase the significance of these biomaterials. Another interesting aspect which is gaining more popularity now is in the organs. Specifically, you are aware many of us need dialysis if there is a kidney failure. If there is an accident, if there is a stone, recurring stones which happen in kidneys, then there is a system failure, and kidneys are vital for us. They are important. Kidney failure is equivalent to death sentence. So dialysis is important. Hemodialysis, each a patient with kidney failure has to undergo hemodialysis very frequently. Initially, there are visits followed by in-house and all those things. So when such situations are happening, the things with which a patient is interacting, the materials that a patient is interacting is a biomaterial. And you look here that the materials have changed from the skeletal system and the cardiovascular system to a more of a polymer-like a component. You see poly quite a few times. You see polysulfone, polymethyl pectine, polypropylene, polysiloxane. So we're talking about polymers. So these are the materials again being used for a simple purpose of maintaining the life of an organ. Another interesting and known application of biomaterials is in eyes, especially in contact lenses. You're aware it's just a transparent film which is put up in the eyes. Then lenses, cataracts are something which are very common in India, with specifically with age. And how are these cataracts get taken care of? They need to be some components are to be taken off, some components are to be inserted. So the components which are being put in are the lenses, different types of lenses, quality of lenses, and these are basically polymers per se. So look at this market figure again. So it is a $7.5 billion industry. Why I'm talking about the numbers is because these numbers are increasing each passing year. I'll give you one last figure of other applications, and it talks about cochlear prosthesis. Cochlear prosthesis basically talking about my ear. Wherever there is a hearing impaired condition, a small component called as cochlea is a goal is to be managed using a prosthesis. Then there can be breast implants on or hernia. Hernia is a condition wherein the organ which was supposed to be there in the body has moved out of that place. There is a cavity which is created, and it is interfering the functionality of the other organ who has to speak very broadly, and that organ has to be put back. So if my intestine has moved out of its pocket, it is a hernia condition. So I need a wall to maintain. So our organs are maintained in their respective places. So these walls are to be again put in or made in such a way that they do not cause a harm to the organs, to the other organ as well. They do not elicit any adverse reactions to the body, and everyone is happy about it. All the cells are happy, the organs are happy, and eventually the whole body is happy, and you can say yes, I'm good and fine. This is the market figure that I was talking about. Why this market figure is important is because this is just an indicative of the fact that the number of patients are increasing who can afford it definitely. And when I say number of patients is increasing, I'm also talking about the livelihood which has increased. The duration of life has increased, and because of which a person who maybe had a life expectancy of let's say 45 years, 50 years back is now going to be till 80 or 90 or maybe even 100. If all goes well. And these conditions are going to be met by replacing some components which have not worked or they have gone bad, like cataract. I'm not staying with my cataract, I want to get rid of it. I will put an artificial lens in my eye, but I want to live in a healthy manner. So that is my objective. So this projection is for the year 2022, and if you look at the growth rate coming in from 2017 to 22, and this table is coming from a projection which was way back in 2017. The 22 figures are expected to change because of this COVID scenario. But look at the constant growth rate, which is on the extreme right side: 3, 5, 6, 7, 8, 5, 7. 5.7, 5.6. So when you look at these figures, it is indicative of the fact that we as humans are willing to incorporate materials so that we can have a good life ahead. So there are various types of materials that can be used, which can be made, and materials which we may be aware of passively, but may have not given it a thought about. So the first is about industrial material adaptation. So we have to look whether the material is made of a component which can be of specific properties. Then we have to also look at for the design of the passive materials. So passive in the sense it should not create its own activities. It should not interact when it is not supposed to be. It should not induce a fever. It should be just there sitting happily, not doing anything adverse. Then we have to also think about the bioactive and the degradable materials. For example, let's say I have to replace part of my kidney with a material so that I don't have to go for a dialysis. And this replacement is temporary because my kidney is going to eventually function, but it is injured right now. So this material insertion and then taking it out is going to be a very painful and difficult process for everyone. Why not have a material which will degrade over a period of time till the time kidney itself is going to heal? So this is what I'm talking about as a bioactive and a degradable material. This degradation happens within the body, but doesn't elicit a dangerous reaction. The components of which it is made, it is going to come out of the body in a very natural way, either through gases, liquids, or solids, but they are not going to cause any harm to the body. Then another kind of material is referred to as a self-assembly material. These self-assembly materials are relatively advanced. There's something which yesterday Dr. Patil also mentioned, utility of nanomaterials in biological fields, various fields that he talked about. So these micro-scaled and nano-scaled materials, they are going to integrate themselves at some level in the body, allow the functioning, and they can be managed to be controlled in some way remotely. Or they can be smart materials. They can go inside the body, they can look around, they can figure out, yes, this is the way I want to assemble, this is the way I should assemble, and then they integrate themselves into the body for a defined function. The last example is a constructive remodeling material. wherein we are taking components of the body, uh, doing some mix and match, and putting them back together. So taking some components from the body, experimenting it outside the body, and putting it back is something referred to as ex vivo experiment, wherein we are taking the experimental part outside the body so that it doesn't harm whatever experimental side effects that may come to the body. And then when we know, yes, it functions because the host cells, like my body part, are working in a healthy way, they are not going to cause any harm, I'll put them back. That is how I can put it in a remodeling purposes. Now, as you understand, we are not talking about one domain of engineering, science, or technology alone. We're talking about various integrated domains, all coming together for one single objective, benefit of the human body. So, just for as an example, if I take the necessary step, let's say identify a condition. So, identification of a condition is to be done by the physician or a dentist, let's say, and they are going to say, "हाँ भाई, आपका दांत खराब हो गया." Now, when a dentist say कि दांत खराब हो गया है, what is the patient going to say? हाँ, सही कर दो, क्या करना है? निकाल दो, दूसरा लगा दो. All these things are going to come into picture. Now, when this thing happens, the doctor is going to, the physician and the dentist is going to discuss with a researcher who will tell if we put this material, it is not going to induce any harm. We have Dr. Patel here with us, who has done a very nice work in this domain, his research work on Candida, wherein he can share the details sometime with you as well, and you'll come to know that Dr. Patel is not a physician, he's not a dentist, he's a researcher. His research is going to be applied by a dentist. He is the inventor of that entire process. But if this process doesn't go beyond it, then the entire milieu of the system becomes useless. So we have researchers, very good researchers, we have dentists, best of them. They are going to be coming together for this simple activity of dental management, and it is going to be supported by various entrepreneurs at different levels. Another example, which typically is of a device design. Now, a physician is going to tell to an engineer, this is what I want, this is how it should be, this is what it should function. Now, engineers, like many of us are engineers, many of us are scientists, once we understand the problem, we start looking at its nitty-gritty. Look at the components, we bifurcate the problem to an extent that we can make a solution. Once this solution happens, we discuss it again with the person who has seeked the problem solution. In this case, let's say the physician. We tell them, see, this is what we wanted, this is what we have made. And then this discussion goes on. It's an interactive session which has to happen in order to make a functional product. This entire process is in the background. At the foreground, we go to a hospital, we tell the doctor, I have a problem in my heart, I'm unable to breathe, so and so. The surgeon takes some necessary steps, and we don't know who is actually making that material, what it is making, how it is making. What we know is, as a patient, whatever materials it is going to be made, it is not going to induce any bad reactions in our body. And when we look at the people who are behind, the researchers who are behind, they are not coming from a single domain. The scientists, engineers are not coming from a single domain. When we look at the materials, we are talking about the people who are expert in ceramics, people who are best in metals, people who are polymer chemists. These three domains are not the same. They are very varied. Many of you are already here who are having some interaction with at various levels with these domain specialists. When we look at the material which is being made, we have to evaluate how good it is, whether it will stand the properties. If I am having a artificial tooth in my mouth, will it sustain the pressure that of my chewing? Like, if you are aware, I don't know, like this, our jaw is the strongest muscle of our body. We can chew anything and everything, whatever. Okay. So what is my important component in my tooth? If I break my tooth and if I replace it, it should sustain the kind of pressure which my muscles are going to give it to. So this material testing is very important. Who's going to do this testing? Now we need people coming from the domain of mechanics. mechanical engineers, we need to test their properties, how good it is, how sturdy it is, how can it tolerate that kind of pressure. Will it change the shape if I give it so much pressure? Now, this thing, changing the pressure is not my domain. I am a biotechnologist. I cannot do this. I will talk to someone who is expert in this domain. By whatever methods that mechanical engineer is going to tell me, you give it that kind of pressure, it will not change the shape. So my tooth is going to be of the same shape the way it was installed by my dentist. Now, I should be also aware that if my material is in my mouth, the artificial tooth, it should not degrade while I'm chewing. If it degrades, then it should not release any toxic components. If it degrades at all. Okay. So I also need to know whether it is going to be causing any side effects to my other parts of my mouth. Will it harm my tongue? Will it affect my gums? These things are to be known to us. So who's going to do this study? It has to be done by a toxicologist. These reactions which are happening by the body at different levels, the protein-protein interaction, the cell-cell interaction, these things are to be done by a cellular biologist. So you understand that we are not talking about one stream at all. We are talking about an interdisciplinary nature. So we need a bioengineer, we need a mechanical engineer, we need a biochemist, we need a cell biologist, we need a veterinary surgeon who is going to perform these activities in a small animal or a big animal to make sure that yes, the system works or not. Then we also need to fabricate this material. This fabrication cannot be done by a scientist. It has to be done by an engineer. So we need a machinist, we need an engineer, and everything when it is done, it has to be sterilized and packaged. So we need industrial designers, we need bioengineers. Then the device testing again involves a lot of similar events which I just discussed. It will require a bioengineer, it will require a dentist, physician, veterinary surgeon, and doctor. So we are talking about so many streams coming in together. Once all these things are done, we need to talk to our regulator. And as a team, we have to propose, see, we have done our best. Now, give us approval so that the patients can benefit. Once it is done by the legislators, by the law enforcers, lawmakers, it has to be put in use by the first person with whom we had a discussion with. This first person was the physician or the dentist. And then they are going to be the ones who are going to use it. And why limit ourselves to one dentist with which they had worked? It has to spread, and then that is how the clinical practice is going to come, and the entire concept is going to be coming to the entire human race. So all these domains are just talking about so many interesting fields. Everyone has a role to play. If I'm talking to another faculty, one of you, uh, I am coming with a problem. You can make a solution. Together we can figure out, okay, this has to work out, this cannot work out. It's not my domain, it's not your domain. Let's work with another scientist, another engineer. So that's how this is an interdisciplinary domain. So if I can just put it in a very small area, per se, to say, we can look at this honeybee womb like structure, and you can see that at the center we have medicine, which is the place the application has to be. And there are two parts that I have divided this combs into. On the left hand side, we have more biology-based components, molecular biology, bioinformatics, synthetic biology, systems biology, computational biology. Some of them based on databases, creation of databases, analysis of databases, analysis of one organ with another organ only based on the information that has been collected over the years. And these are supposed to interact at certain level. And on the right side, you see nanosciences, chemistry, tissue engineering, mechanical engineering, material sciences, IoT coming into picture. So these are the domains in which we are going to see the application coming from. Various solutions also pouring in from these domains. We can also see we have some, I have put in a couple of blank hexagons, and this is just to share that we don't know who we require. We may be requiring some other person who expertise which I am not aware of right now. And therefore, this is a continuously evolving domain wherein the contributions made by each one of you, literally each one of you, is going to be useful. So, coming back to a different level, what all research has been done in biomaterials domain? Now, so far, I will share in my next slide as well. The evolution of biomaterials has been based on requirements of the person requiring it. For example, if the requirement is coming from a dentist, the dentist was the one who was also the inventor, who was also the applicator and the consumer and the customer for that product. The consumer being the patient. So it has been majorly towards biomaterial synthesis initially. Its optimization, characterization, testing, and the post-material interactions, if it were all they were there. Now, this has been the notion so far in the initial first two generations. Now we are looking at the future wherein we are also talking about materials which will not only elicit this desired reaction, they will elicit this required reaction at a specific time in the way we want and in a time when we want. Although these are going to be spatially and temporally controlled at a different level. And that is what I am referring to as smart materials. Some of you may be aware that some materials react differently at different pH. Materials change their features with change in temperature. These conditions may be externally controlled or may be evolved as per the requirement, and that is where a material has to function in the way it was intended to. So that is the current effort that is going on in the research domain of biomaterials. So this is the evolution of biomaterials that I was talking about. So the first generation implants were ad hoc implants, wherein the physicians they were not discussing many of the things, but not as a research, but they were also doing their own research. For example, uh, taking the example of dentistry again, a very common domain to start off with, you may be aware that couple of decades back, if we consider maybe our grandparents or their parents, if they had any cavity or a related issue, they had a gold capping, and that capping is not seen right now to the extent that it was seen then. So who made that gold? Who made that capping? Was there any engineer associated, or it was just the goldsmith and the dentist? So obviously there was limited interaction. The communications were limited, and not by requirement, but it was not thought so that there will be some other disciplines which can be made use of. So initially they were of gold fillings, then there were wooden teeth as well. And later on, there were some materials which were identified by the dentists who said that it is not going to react with anything else. In the same way, there were bone plates which have been there. Bone plates to replace the bone if it is fractured, if it is literally mashed up and the bone cannot be retained back. So there was, instead of bone, let's have a bone plate. Then something that you may be aware of, a glass eye. If the eye has gone bad because of some accident, injury, disease, whatever, so take out the eye and put in a glass eye. Obviously, a person is not going to be able to see it, but the function of the rest of the body, the aesthetics are maintained. So these were the first generation implants that have been witnessed by us. These are the examples, intraocular lenses, more advanced version. And in the left side, you can see this transparent like thing which is present in the eye, and it is held back in its position by two arcs, one at the top and another at the bottom, which are holding these material into a specific site. And if it is taken out, this is how it is going to look at. The transparent gel-like material, it is a silicon-based material. And on the right side, you can see I have put in vascular grafts. So these grafts are basically going to be replacing the blood veins which have been filled up, and they are now choked because of accumulation of various fats or fatty acids or lipids or cholesterol, whatever you call it. So these grafts are basically going to be the blood vessels which will need to be replaced, cut it by the surgeon and put in by the surgeon, made extra, made not by obviously the doctor, physician, but by some scientists and technologists. Now the second generation were based on now an more exposure of the worlds with the scientists, physicians, technologists coming together to make an improvised version. These are the things that you are actually now able to witness right away. In fact, if I go to my dentist and I say कि दांत खराब हो गया, instead of a gold gap, I put in a titanium alloy instead. So this is the generation that I'm talking about, and I'm sorry for the typo. It's not the example of the first generation. It is example of the second generation implant. So there are other interesting second generation implants as well, like the heart valves and the pacemakers, which are now available. So what we see are basically the second generation implants across the world right now. The third generation is something which is coming up, and it is very limited right now. It is being focused as the smart materials, and there are very dedicated centers and institutes which are making them, and they are what are now referred to as the cutting edge technologies in the domain of implants. So what are we talking about? There are some limited examples. For example, skins growing on our skin. An artificial skin is growing based on the inputs being given by our body, so that it replaces or it makes the new skin. For example, a skin which is burned, there is nothing to grow on it because the tissue is absent. There is nothing to start the base upon. So therein, this Integral Life Sciences has come up with an interesting solution called as artificial skin. It, I don't know to what level they have launched it in the market and what is the cost, etc. But that is something very interesting. When you, there are various places where skin is required, which is lost by various reasons. Maybe it could be a fire. Person getting burned could be the one as a victim, or it could be the person who's actually fighting the fire as well. So when we are looking at artificial skin, we are also looking at various reasons why the skin itself is not growing. So this artificial skin is supposed to be there, function in a similar way. What is the similar way? Like it should be sensitive to various other features like temperature. It should be sensitive to the water with which it is interacting. Obviously, it may not undergo, it may not sweat right now, but eventually it should be able to take care of that scenario. It should just not fall off the body if there is too much secretions of the sweat. Now, Genzyme is making cartilage like material, which is going to come into places where cartilage is lost. Like cartilage is difficult to be synthesized by the body once it is made. And cartilage is basically the components which you find on the top of the bones. So these are materials which are acellular. They do not have lively components, but they are once it's synthesized, they are rarely remade. So these companies, these companies, they are trying to make cartilages which are going to be produced by the cells. So how we are going to elicit the cells to produce a component which it does not want to is something which is quite interesting, and it is the future that we are looking at. Just giving you an example, and this is something which I want to definitely share, is about heart valves. Now, heart valves are pretty expensive. When I say expensive, I'm talking about 5,000 to 8,000 onwards. This is the international price that I'm talking about. Now, India has produced the Chitra heart valve, a very popular one. And if you can just look at the amount of time it required for this research is 15 years. 15 years of research, and now we have a Chitra heart valve, which is now being commercialized by TTK Pharma. And TTK Pharma is the third company in the world to make the heart valves. It is the third company basically coming from this institute in Thiruvananthapuram. And when you look at the price, it's $350 approximately. And this price is, I think, 2018 or so. I don't have the recent price. But when you look at the cost in Indian rupees, it comes under rupees 30,000. And when I look at the international cost, it starts from 5,000 to 7,000. Onwards, it can go up to 16,000 as well. So where do these costs stand? Just look at the cost. See, something at 5,000, the minimum. 5,000, we are reducing it to $350. It's made in India product. It's one of the reasons why India has become a medical hub, because the cost is very important. And you can see this person holding the heart valve, the size of it. And the material which is used is ultra high molecular weight polyethylene. It is a polymer that I want to emphasize here, that many materials that which are made available are coming in the domain of polymers now. And on the left side, you can see it's a blood bag, one having blood, another having serum, another having plasma. And these are all again coming from this interesting polymer called as ultra high molecular weight polyethylene. So what we have looked so far on the evolution of biomaterials is its structural nature, initial, the first phase. The second was of soft tissue replacement. And the third one, which is the recent, is the functional tissue engineering constructs. So this aspect is going to be covered in the next session as well, and hence I'm not going to discuss more on this. And I want to show you this person. Many of you may be aware of reading this news coming in last year, in the last 2 years. And he is Dr. Peter. And Dr. Peter was diagnosed with motor neural disease, which basically means he had 3 to 5 years at most, and then he was supposed to die. Okay, so he took a decision, he and his partner, and he had this issue in his thorax. So he could not drink, he could not eat, he could not do anything. Obviously, he had a motor neuron disease, and then he took a decision of changing his life by switching off from some biological components and moving on to some artificial components. And then he announced on Twitter that Twitter 2.0 is now online. So that was his tweet. And just look at the conditions that we have made. He's considered to be one of the initial cyborgs of the human race. And this is something which is necessitated by the will of a person. Doctors had given up, but not him, not his partner. The two doctors themselves made this entire process. In 3 to 5 years, when he was supposed to die, he switched himself into a newer version, not completely human, but an assisted version. And he claims that he will at least survive till 80 years of age. So you can see where we are going. This is just one example. There is some crazy youngsters in US also did a similar thing, not with respect to saving their life, but rather installing. Both of them were DJs, music jockeys, and they installed controllers in their wrists. And it was just to make sure that they are able to control it whenever, wherever they want to. And you may be aware these implantables are now a thing. So when you look at the human body as a whole, just look at the various places these lines and dots are hitting on the human body. These lines and dots are the places for which we have options, solutions to be replaced, which are either already done or they can be made, and we'll be seeing a new version of ourselves in some time. So you may, if you are you have been looking at movies, you may be aware of this movie called as Terminator with Arnold Schwarzenegger. And he was a humanoid in that movie, and you could see, if you have followed that movie, the skin was real, the inside body was a robot. So it is just one of the components of this thing. Or if we look at the human body, we have deep brain simulations and brain to machine interface which are being worked upon. We already have cochlear implants and the hearing aids. Bionic eye is something which is in making, very much in advanced stages. When we look at fracture repair, we are almost there. We don't need new research because we can take care of many of the fractures already. Vagus nerve simulation is something which is quite interesting because it allows a lot of blockages to be taken care of. Artificial heart is something you may have seen in various times in newspapers coming in and going out. With the artificial heart already in place, it's going to be very soon that we can see artificial heart. We already have breast implants, we already have heart pacemakers and defibrillators. Now these defibrillators are also coming in implantable way as well. So instead of having an external defibrillator, it can also become we are going to have under the skin. Then there are so many others when we look at, and the lower side we have artificial foot. Yes, we have artificial foot, we have prosthesis and orthotics, totally dedicated stream in it. We have artificial skin coming, we have artificial legs, knees, we have bionic eyes, we have bionic hands coming in the picture. The RFID tag, radio frequency ID tags, which are going to be, which may maybe 50 years down the line, instead of Aadhaar card or a citizenship card, we are going to have a RFID card in our hand. That's going to happen. We know about it. So when we know about it, what are the materials, what are the sciences, what are the technologies that we are talking about is something which makes us more strong. So we now move on to various components of the biomaterial. What all things we need to look at. What are materials are to be looked from different perspectives. So here you can see that I have put in some interesting features, some boxes, which I'm going to talk about. So these are the integral components or the integral subjects of biomedical sciences. Some of them I have briefed upon, some of them I'm going to talk about in detail. Let's look at toxicology. So toxicology is basically the sciences which works on the concept of whether the material is toxic at some levels or not. If I am making a new material altogether, I have to make sure that it is at least given at 2000 mg per body weight of a small animal. I am talking about toxicity at 10, 20, 30 times the levels they are supposed to be permissible. Why am I talking about that? Such levels? Because if the material is taken up accidentally or consumed accidentally, it has to be stable and not induce any toxicity at any level. So that's what the toxicity is all about. Whatever biomaterials I'm working with, whether it is metal, whether it is ceramic, plastic, polymer, blends, whatever it is, they have to be non-toxic. If it is a polymer, you understand it may be broken down at some point of time. So whatever polymer which has broken down, when it leaches into the system, basically the human body, it should not cause any problems in the cellular systems. The next is the mechanical performance. So the mechanical performance is basically the strength that I'm talking about, like I give an example of the tooth. If it is a plate, this plate is coming in my arm or wherever the fracture is, it should be able to sustain that pressure. It should be able to have an equivalent value to that of the bone. So if I'm a child, if my body size is 8-year-old, then it should sustain that size. As the body grows, it matures into adult 28-year-old body. It has to be replaced, and the replaced component should be having the strength and performance as per that of that age. If it goes beyond that, no issue, no harm, but it should be definitely not be less than that. It should be durable for a very long time. We are not talking about exchanging the plates every now and then. If it is there, it has to be there. Ideally, it should be there till the end of the life. Next is the biocompatibility. Biocompatibility talks about the performance or the success at that doing that work. Okay, so basically the biocompatibility can be defined as the patient is alive so it must be biocompatible. Okay, so that is how we look at biocompatibility sometimes, but that is not the all. Biocompatibility is not only about whether it is available, whether it is not available to the body. It also means that it is not inducing any negative reactions. When I'm saying the negative reactions, I'm not talking about toxicology. I'm saying that the system is there, but it is also interacting with the host body. But the host body is not going to be killed because of it, and neither the system is going to be rejected by the host body. So this is the biocompatibility that I'm talking about. You may be aware that whenever transplants happen, there is have been a risk of uh, failure of the transplants or rejection, something which biologists refer to as, or medicine people refer to as, graft rejection. So when these materials are going to be put in the body, it should not be rejected. The body should not elicit a cytokine storm, or it should not elicit a fever or anything. It should not do anything negative to itself. The body has its own immune system. The body fights. We have been fighting COVID for quite some time now. Many of us have been infected. Many of us have recovered. The reason being, we are fighters. We have our own system, defense system working on it. These biomaterials should not be considered as foreign or alien to the body, and that is what biocompatibility means about. Next is about healing. So healing is whenever we are putting in a tissue, external entity, we are also going to induce some harm in order to deliver that material inside. So when you are talking about delivery of material inside, let's say if I am talking about joint replacement. For a joint replacement, I need to cut a part of my body. From the surface, go deep inside, take out something which I want to replace, put in the replaceable biocompatible biomaterial, and then fix it, whatever I have cut in. Now, in doing so, I have induced a local harm as well. So this biomaterial should stimulate a reaction which will, instead of uh, slowing the healing process, it should induce, or rather not do, a non-healing activity, in the sense that this biomaterial should elicit a response from the host that it should start healing itself. It should give an indication, yes, all is well. Go ahead and heal yourself. Let the knee skin be healed. So that is what that reaction should be. It should not be inducing any inflammatory reaction. Inflammatory reaction is basically a defense mechanism by the body, wherein the body starts activating its armies of white blood cells and tries to kill off and remove any such foreign entities. So the biomaterial should be able to heal the injury. Then there is something which is referred to as functionality. Obviously, the biomaterial should be functional. It should not just be there and there. It should not be just useless. It should do its activity. It should be functional. It should not degrade. It should be stable. It should be durable, and it should do its activity. Then the anatomical site of the implantation is critical. Obviously, the word itself tell you what I'm talking about, meaning the shape, size. Which literally, when I say shape and size, I'm talking about the entire geometry. So when you look at the bone implants, the ball socket joint that I showed some time back, it should have the same features of that of a bone. It should function in the in a way that it will not cause loss of function, and it should be in a similar functionality with the same dimensions if possible. It should have the same mechanical strength and the properties and the bioresponses that it should have. If it would not have been a biomaterial, rather it could have been a uh, natural material also. So the mechanical properties are something that I have discussed. Ethics is something. Ethics and regulatory are something which are fluidic in nature, I'll say, because ethics change and evolve over a period of time. Something which may not be ethical right now, or may not seem ethical right now, may be appearing ethical sometime at a different place and a different time. Just for example, it's an example. If I say that the average lifespan has increased over the years, if if I would have been living in an era where people over the age of 50 do not usually live, and if I am 50, I would have been preparing myself to die. But today, if I am 50, I will be planning my retirement at the age of 60. I am planning my retirement. I'm not planning my death. Okay, but this concept has changed over a period of time, and that is what I was talking when I said that ethics are fluidic in nature. They change, they evolve over a period of time. Today, we want our parents, grandparents, or persons who have injured to heal well within time, and we may be the people uh, who may take that decision. Yes, put in a stent right now. That person is on bed. I don't want that person to die. We may be the person who are giving the consent. It may be ethical for us. It may not be for the person who is on the bed right now. That person may say, "कि मेरा time आ गया है, मुझे जाना है." So these ethics are something that we need to understand, and not only about the humans but also about the animals as well, because when we are doing clinical trials, before that we need to do preclinical, which is on the animals, and animals being our literally soft targets and experimental places. These our experimental designs have to be in a way that we use minimal number of animals, and they are well ethically let off. The last is the regulation. Regulations are dependent on the country, wherein these materials are made and wherein these have to be implemented. For example, we have US FDA for the US, we have Indian FDA in India. Indian FDA is divided into basically coming out a fresh one a couple of years back itself, and it has given authorities to the local state government itself. So if I'm in Maharashtra, I'm talking about Maharashtra FDA. If you are in Rajasthan, you have to talk about Rajasthan FDA as well. So in the same way, there are some other standards as well, like ISO, International Standards Organization, which also gives a fairly good level of quality across the globe. So all these things, right? Toxicology, mechanical strength, biocompatibility, healing, functionality, anatomical site of implantation, ethics, and regulatory, all these eight, these are the integral components of the biomaterials. So, what are the components? Again, they are metals, alloys, ceramics, composites, and polymers. Just an example, time and again, I'm just repeating myself. Metals and alloys can be used for dental implants, stents, orthopedic implants, orthopedic screws. For ceramic, we have seen its use in bone replacement, heart valves, dental implants, joint replacements. Then there are something which are considered as composites. Composites are when metal, alloys, ceramics, and or polymers. There's a mix and match of any of these three domains. These are called as composites. And if I'm using any two domains together, let's say metal plus metal, let's say alloys, or one ceramic plus another ceramic, or one polymer plus another polymer, that will be referred to as a blend. So that is why I said there are 4 to 5 types of biomaterials. Three are uh, pure, composites involve any of the three, and blends are the ones in which involve two of the more of the same kind. So these materials are something that can be a very long system, and instead of going into each one of them, I'm going to shift gears and discuss about the biomaterials which is derived from waste. Why I'm talking about waste? Because waste is something that we generate passively. We are not aware of that we are generating, but we are so used to our lifestyle that we generate a lot of waste. And since we have to be in a sustainable mode, why not use this entire waste for our own welfare? So there are various advantages associated with using waste for biomaterials. Obviously, you are aware of many such examples in your respective domains as well. So some of these advantages are common to various applications. But right now, I'll just simplify these advantages for biomaterial use. So many of them are clean and a simple process. Many of the materials need not be made altogether. They need not be synthesized from scratch. when we are using a waste, we may just be tweaking the processes, cleaning the materials to get the right composite or the material that we are interested in. Now, there will not be any non-toxic degradation. They are definitely going to be biocompatible because the way we want them. They are also coming from mostly from biological sources. In order to be successful, they have to be cost effective, and it also reduces the waste which is generated during the process, and at the same time whatever was the input was itself a waste, so therefore it is going to be waste minimization, and we need to definitely use renewable resources in order to achieve it. So now I'm going to share some big charts with you, and from waste, and I'm just going to focus on a couple of examples for sake of simplicity, and just to give you a platform to share that yes, we can use this material as well. Okay. So here I'm talking about marine waste. So the significance of the marine waste comes from the fact that of the total of 100% of the marine components that we use for our consumption, especially fishes, whether it is shellfish like shrimps or soft fishes, non-shell fishes like rohu, katla, or whatever. 26% of these become waste. So imagine if I'm making 4 chapatis in a day, one chapati is going to be waste. It's such a shame that I will be in, that if I come to know that I'm making 4 chapatis and one of the chapati is going to go waste. So you can understand that whatever the level of waste we're talking about. And marine fishes are the ones that are most consumed in the world, because we have a lot of abundant space that we assume we own it. But when we look at the wastage, it is 26%, quite huge. So what all things are there in this waste and what all can we make out of it is something which is presented here. So there are a lot of shell fishes and there's shell components. For example, mussel shell. Mussel is the one in which we get our pearls from. So the hard coating which is there and the soft organism which is sitting inside and making that pearl, if it dies, if it is to be killed because of the pearl, what is going to happen to its shell? It's going to be a waste. In a similar way, we have cocktail shell, then components coming from the jellyfishes, then fish processing industries, cuttlefish bones. There are so many of them. If I just start telling about the oyster shrimp, the shrimp, there's so many. So there are components in them which are hard, ceramic like origin, and they are abbreviated as HAP and beta TCP. Beta TCP is beta tri calcium phosphate, and HAP is I'm just not able to recall it as uh, polyhydroxyapatite. I just lost that one. I'll come back to you on this. So just a second, I think. Yes, is my screen visible again?
Yes, sir. Yes, sir.
Okay, great. Thank you. So these materials, HAP and beta TCP, they are going to be used for the formation of the bone. So the artificial bone that I'm talking about. In the same way, collagen, which is coming from jellyfish, can be used for cartilage regeneration. So these two are the major applications that when we look at marine waste, can we make the new bone? Can we make a new cartilage? So I'm just going to give you a couple of examples on this subject, and then we'll go to another waste. So yes, HAP is hydroxyapatite, and here in common waste which is generated even in house, like egg shells and she shells. What this group of Hembrick Holloman did pretty recently, in fact, is that they dissolved these shells into a solution, and they used 3D printing methodology to make a structure which had similar features as that of a bone. Now, in this cartoon, you can see on the left hand side there's a small flask in which this egg and the seed shells, they have been dissolved, and now we are getting a monomeric substance or the starter material which is required for the formation of or is equivalent requirement for a bone. So how to make a bone? They have used a very novel approach here. They have made this liquid solution in a way that it can be printed in a at a temperature and at a condition that will give rise to a architecture which you can see on the right side, a small rectangle square-like materials, which when we look under the microscope have a lot of sheets crisscrossed over each other. So these architectures are sufficient to put in as a bone replacement in a body, and they are hollow enough to allow the healthy cells, the stem cells of the body, to go inside, make their own niche, and develop the environment into the one which they already are used to. So development of this microenvironment requires the material to be hollow, not reactive at all, and this is what they have made. So quite an interesting use. Anyone who has been eating eggs, the amount of waste which is generated every time these eggshells are there, and it is not very easy to degrade them naturally as well. But here in these group of researchers identified a novel way of turning this she shells and egg shells into a bone-like material. Another similar example is coming in from the waste muscle shells. These waste muscle cells are basically coming from the artificial diamond generating industries, wherein these dead muscles they are taken out, removed, or they are maybe also coming from the restaurants business as well. And these shells are very hard. If you notice, they are not very easy to break off as well. Some of you maybe have seen these or used them in their mirrors, especially if you go to any island country or a beach place. You see in a lot of interesting materials being made of these shells, jewelry, mirrors, boxes, gift items, etc. So you know that they are pretty hard. So when you know that they have good strength, what can we do? Because they are not going to just degrade into the earth. So they are one such material. Another material that this group have used is called is a squid pen. So squids don't have a external skeleton like muscles there, but they have an internal skeleton system which is called as a pen. This pen allows them to have their sense of orientation, and it is basically their skeletal system. So this pen is a small, thin cylindrical entity, and herein, in this paper, these researchers have used these mussel shells, the squid pens, and the crab phytosin. They have digested it with some reagents like ethanol, acetic acid, glycerol in some proportion and all, or crushed them physically as well. Then they have blended them in a specific shape, and that shape can be used for bone tissue engineering. Very interesting thing, because making a bone is a very long process. So instead of making a new bone, why can't we just pour a liquid of yeast composition and allow the bone to be formed? Now this bone is going to be of a similar structure that I showed in the previous slide, wherein you can see that it was a hollow structure, and in this hollow structure the cells would just seep in at some point of time, and after seeping they would make their own ecosystem for their own sustainability. Now second waste domain which is commonly available is the plant waste, which is derived from which can be used to derive biomaterials. Now plant waste is something that many industries are working upon, which includes cellulose, pectin, gelatin, and others, which are generated by various industries. And when we look at them, there are various certain components from where they are originating. For example, when we talk about cellulose, the leaves, peels, and the seeds, they are the major sources. Pectins, they are coming from the peels of simple fruits, or the pomace. Genicin is coming from the flower. So here I am showing an example wherein the lemon peel, which is rich in pectins, it is being used to prepare this scaffold. Wherein you can see that our regular peel of lemon, in fact, you may try it at your end as well. You can, instead of lemon, you can try orange or citrus fruit. Whatever waste which is generated, you are aware that it has its own aroma, its own flavor as well. So if you dry it off, which is pretty easy. You can powder it, and once it is powdered, you can extract the pectin. So what will you do with this pectin? This pectin can be used to make cryogels. Now, cryogels are basically hydrogels which have been prepared using temperature as one of the reaction components, and because of which temperature, I mean cryo temperatures basically. And at this temperature, the material is going to be formed as a physical inducer. So this pectin is going to be also can be used to form other scaffolds for the body. Now another example is of genesin cross-linked with piperidine, and herein hydroxyapatite (HAP) is going to be used as a tissue for bone replacement. So herein what the gray colored images that you're seeing right now, they are hydroxyapatite and bone tissues at different scales. So you can see that if you compare the architecture is something which is smooth. It has a lot of components in them, and when you compare it with the image on the on the left side, which is coming from the bone, you can see the structure of one of them is almost the similar. As we go at a higher magnification, obviously they are going to be nitty-gritty changing, but you can see at a broader level the structure remains the same. Next example is of a livestock waste derived applications, and herein you can look at what are the components that are being extracted from, what is the waste type, and what could be the application. So the extracted compound is usually the calcium phosphates, like coming from the eggshells, and the hydroxyapatites, which I just discussed for marine derived as well. Then a second such example is keratin. Keratin, you are aware, it comes from the hairs, nails. In case of animals, we know they have hooves and feathers. And the last one is the hyaluronic acid. Now, hyaluronic acid is a very interesting compound, and if anyone using cosmetic creams, they must be aware that hyaluronic acid is the one which comes in that serum to give you that for the creams or gels which claim to reduce aging process. So hyaluronic acid is basically present just underneath the skin, and as we age, the amount of hyaluronic acid decreases, because of which we get the wrinkles. So it is very popular in the cosmetic industry, and whatever kind of cosmetic surgeries that happen, they basically involve one level wherein hyaluronic acid is inserted just subcutaneously, so that freshness or puffiness is coming back into the skin, which does not showcase the wrinkles. So you can see that these three types of waste are generated and can be extracted from various sources, and their applications are pretty straightforward. If we are getting eggshells and bones, we can get the calcium phosphate and the hydroxyapatite out of them. And what will we do with that? We can allow them to grow on a scaffold-like material, develop them into scaffold-like material, so that biologists can work at the biocompatibility levels. They can also be used as a replacement sometime soon for instead of metals being present, we can use these calcium phosphate or hydroxyapatite materials in place of these bones, which are to be replaced. Now, keratins are being used for development and growth of fibroblast cells. Fibroblast cells are one of the type of cells of the body which are responsible for generating the like they are the nursing cells, so as to say. They generate the kind of environment which is required for other types of cells to grow. So if I have to grow a stem cell, I should also be having some amount of fibroblast cells, so that the stem cells can grow themselves. Okay. Then hyaluronic acid, one such application I told you is on cosmetics. Other applications are development of hydrogels as well. So one example that I'm going to discuss here in this research article is wherein the eggshells and chitosan coming from this young crab, it was taken and the components were dissolved by some specific reactions and the materials which were interested, hydroxyapatite to be specific, they are dissolved in a solution and then they are put in a small dish like component wherein human cells like SAOS2, the SAOS2 cells, which are basically precursor for the bone formation cells, which is called as an osteoblast like cell, is cultured onto it. Why should SAOS cultures be cultured onto hydroxyapatite is because even they need a precursor of something similar to bones. Once they feel that the environment is right, they can start producing bone architecture on its own. So what I'm saying is, in order for the cells to be mimicked into the environment, the host should be suitable enough to allow such integration to happen. So the future of this research is basically to showcase that if this hydroxyapatite is put in a environment wherein the human cells are available, they are ready, they are viable, they will differentiate and release hydroxyapatite material so that the bone can be reformed. So that is what I'm talking about, and that is the interesting thing that we are looking forward to in the domain of biomaterials. The next is utility of pig bones, which are generated in the slaughterhouses for development of the exact same hydroxyapatite. And herein, you can, this is a simplest flowchart that was possible, wherein the raw bones are taken, they are cleaned using hot water, and the protein levels are removed. So it is called as deproteination. Then it is crushed, pulverized, heated up to make a solution, and small pellets are put in a different pressure and temperature, and what we get is a scaffold material which is made up of hydroxyapatite. Next is I'm moving to hyaluronic acid. Now the abbreviations are almost the same, HA, HAP, or HA here. So HA here stands for hyaluronic acid. This hyaluronic acid is coming from Coombs rooster, and it is pretty expensive because when we look at the human applicable grade, this has to be not 99% pure, it has to be 100% pure, because even 0.01% levels of impurities is going to cause lot of immune reactions. So this hyaluronic acid is present in lot of places in the body. Like you can see here, it is present in the heart, it is in the eye, it is responsible for the wound healing, which is on the skin. Then the smooth functioning of the bones is because of the fluid which is present in between these, and that is because of presence of these materials. Now, and it is also required at some levels in the brain and in the lungs. Now, if we can make this artificial hyaluronic acid, we have a lot of ways and applications to go ahead with. Okay. So this is just an example that can be looked upon for development, whoever is interested in hyaluronic acid. And I'll just skip this slide. There's something again on industrial waste as well. I think I have like 10 minutes more, and I will just go ahead with this. There's a soy protein and chitin sponge like scuppers, which can also be utilized for biomedical applications. You can see that this person is holding the sponge in between the fingers, and you can look at the edges are light colored and the center it is a little bit dark colored. It is because of the sponginess which is of this tissue. And below you can see that in the black background we have a cell which is green and blue in color, and this tissue is growing healthily in this environment. So we can make tailor-made polymers from the whether leather-based valorization process as well. A lot of polymers which have a lot of applications as well. These polymers could be natural polymers, they could be synthetic polymers, or they could be polymer composites altogether. And they can be made by various processes. The place is still young for research, and recently there are polysaccharides which are integrated with nanomaterials as well. And this is where different streams are actually coming into picture and merging all together. Wherein you can see this is a cellular, what you see here is a cell surface. A cell surface looks like a lot of beads on the top, and there are some big potato-like things which are present in it, which are called as integrins, and they are networked with others with the help of collagen fibers and fibronectins. So here in proteoglycan complex consisting of the carbohydrates and the proteins and the polysaccharides, they are actually interacting with each other, and this is where the nanomaterials are now being focused upon to how they can integrate in these lines. This is an example of scaffold hollow material, which is when we look at it at higher magnification, which will allow various types of cells, different colored round things that you see here. There are different types of cells, and if you look at various Y-shaped structures, they are cell binding ligands, which will allow these cells to go and bind to these scaffold-like materials. In the lower cartoon, you can see we have a similar entity coming in the whole bone, and in this tissue architecture, when we look at, we can make these components. If we look at the extreme right side, which includes hydroxyapatite and the collagen triple helix, these are the components that can be derived from the various wastes. And if we just follow the arrows in the inverse direction, from instead of going from left to right, if you consider that you have the hydroxyapatite coming from eggshells, shellfishes, etc., we can start building it in from right side to the left side, which will eventually go into the full bone structure. These are some of the references that you can look at, some very well established editors who have come up with different editions. Some of them are classical journal references now, which are present. The left top corner, blue one, is the most recent, and this is from where I have taken a lot of material as well from. And these are the journals wherein you can look at further research if you're interested in biomaterials. Biomaterials is from the Elsevier House, Journal of Material Sciences and Materials in Medicine. I think it is from Wiley. And the third one, Journal of Biomedical Materials Research, Part A and Part B, both of them, they are also pretty good. So that's it from my side, and I am open to questions and suggestions. You can contact me on this. My current research domain is in using these biomaterials for their integration into life system. Although I come from a background wherein I've used cell systems, but now I am using my knowledge of growing cells and applying them into various types of materials which can be used. Thank you. I'll just stop sharing, and we can have a discussion based on this. Hope I have not made you sleep with my monotonous presentation.
Thank you, sir.
Please.
Thank you.
Thank you, Dr. Sharma. If you have any queries, put in the chat box, or you can ask me live. I'll be happy to answer them where possible.
Good morning, sir.
Good morning.
Sir, I just want to query about जैसे कि while replacing the joint, which polymeric material we should prefer, because one of my colleague, one of my known has just now replaced their knees, and they have polypropylene options, silicone option, or many other doctors just want to discuss with us that which kind of material do you want to replace in your joints?
Dr. Shweta, I totally understand your sentiment. It is funny that they ask, I will say, at the first, because we are not so much aware of what all properties of materials that they want to tell us. It's basically it's your choice. Basically, I will say the material of choice is all of them. When they have come out for commercialization, they all have been evaluated at all the levels possible for the quality, the strength, the toxicity, etc. So, if you are considering yourself for if you have to give a suggestion, then please look at what all features that you expect yourself to use it for. For example, if you are that joint replacement, if that joint is going to be very much going to be in use, for example, if it is hip joint, and if that person is going to be running around a lot and not going to be sitting at home at one place, then the quality is going to be definitely slightly of more, a fraction more. I will not say that it's going to be fraction less is going to make more difference. It is just that the wear and tear or everything is definitely checked in for a very long period of time. But look at various other aspects as well, including the cost.
Definitely, we have preferred the lightweight polypropylene-based joint. Johnson and Johnson company has provided that. That's why I just select that. Being a chemist, I can select that a polypropylene-based lightweight, and the company is also taken into consideration that the Johnson and Johnson's is providing that. Howsoever, it is very costly compared to
Yes,
others.
I totally agree, and Johnson Johnson is one of the major players in the market for joint replacement. And as a consumer, you should be aware that there has been some defects which have come up in for Johnson Johnson, which Honorable Supreme Court has raised issue a couple of years back, and Johnson Johnson was the one which had to comply, and there was complete compensation for that as well. So I don't know the exact joint which that you're talking about is the one which was in the dispute, but Johnson Johnson is now acting responsibly for that issue.
So may we know any Indian company which is going to, produce such kind of joints in future? We can be aware about that.
Yes, definitely. And I'm sorry I don't have that information with me. I can definitely look and come back to you on this. But joint replacement is something which is being worked upon very aggressively by many industries in India. However, when you look at the consumer market, it is very difficult to penetrate these markets. I have had my first-hand experience as well when we launched our products. Market entry of the local low-cost players is very difficult, and that's where I shared the example of Chitra Hardcore, because it was the third company to launch it, and at a fraction of cost, and they are just lucky to survive the kind of pressure they have been in it.
Okay, sir. Thank you so much.
Yes. So I have a question from Pratiksha, which says, what is the feasibility of large-scale production of bone-like materials from sea waste like chitosan and eggshell? Thank you, Pratiksha. That is a very important and a critical question, because that is where we as researchers stop and innovators and entrepreneurs come into picture. The feasibility is looked at different scales. What is the source from where it is being procured? For example, if I talk only about eggshells, then I need to have a lot of eggshells to start making a cost-effective material. So making a large-scale production is goes outside the domain of science and technology. It goes actually into the domain of management, wherein procurement of raw materials is very much critical for establishment of such an industry. As a POC, yes, we know eggshells can be used. We know, yes, marine components can be used, but we don't know who's going to do it and how it is going to be feasible. Yeah, Pratiksha, I hope I answered your query. Any other question or any discussion?
Thank you, Kapil sir. That was a very interesting talk. I very much enjoyed it.
Thank you, Dr. Mandar.
So participants, if you have any questions, please. We still have a few minutes left.
So I have a specific query, Dr. Swapnil. Very good presentation, very much informative.
Thank you, sir.
So how we can enhance the mechanical strength? So any thought on those lines?
Yes, so mechanical strength is something that can be worked upon by two mechanisms. One is by doping the components, like specifically which is called as a blending method, wherein different materials, whether they are ceramic, polymers, or alloys, they can be merged with each other so as to increase their strength, mechanical strength. Another option is to increase their density by working at the level of their fineness, basically. So the way I am making a biomaterial, if I can tweak it to make it more dense. That is one way that I can think of right now. But if you can say that if you want to specifically work with, let's say for example, polymers, then one good method would be blending.
Thank you. Really appreciate. Dr. Pavan, you were about to say something. Dr. Pavan, please.
So can I ask something? Like,
Sure, ma'am. Sure.
it was really very good presentation. So just now, Nandi sir raised the issue of improving the mechanical strength of biomaterials. So like I was just thinking like if we consider a human body and like if we want to increase the strength of like if we are lifting something very heavy or something like that, then what we naturally do is we hold our breath. So we make use of that compressed air to improve the strength. Can we incorporate something similar and have some smart material where the air can be compressed to improve the mechanical strength?
Yeah, ma'am, that is a very interesting concept that you have put in. Yes, I agree that holding breath is what is practiced, but it is not the way that it is done. Holding a breath is just a physiological process that we do. For example, if instead of lifting a weight, if I have to run, I cannot hold my breath if I have to run because I need to continuously breathe as well. So what I can to some extent understand and extrapolate as well is improvising our strength using materials is definitely something that I've been many people are working upon. But that is not through utilization of biomaterials inside the body. It is being considered outside the body, and what is now referred to as an exoskeletal system, wherein the strength of the body can be improvised to a level using robots and mechanics outside the body. Inside the body, it may not have the same utility because right now the current ethical practices, we are not allowing ourselves to improve our strength as of yet. What we are trying to improvise is only a replacement activity. For example, if my needs to be leg bone needs to be replaced with a plate, then it should provide the same kind of strength. And if I am a runner, if I'm a sprint runner, my strength should not be enhanced only because of bone being replaced by metal plate. So that is not something which we are considering as ethical right now. Definitely, it is the future wherein this ethics will become redundant in some point of time, and we become more of a superhuman being because of improvisations of our physiological processes.
Thank you. Thank you for clarifying, sir. Thank you.
Yes.
So, madam, you can close the session. This is already 11. We have another session 11:30. Good discussion is being done. You can close the session.
Yeah. Thank you. Thank you so much. Thank you all.
So, thank you, Swapnil sir, for